What's up, everybody? Mr. Kozad back with another video lesson. Gotta tell you, today is a great day to be alive. I love this lesson that we are about to do. Okay, this is part 2 of a 2-part series on graphing rational functions. And man, if you didn't watch part 1, stop what you're doing. Part 2 is not for you. Go back, watch part 1 first, then come in part 2 and get it done as quickly as you can, because part 2 is so much fun. We're going to talk about things like hiatus points. Those are holes in the graph. We're going to talk about slant asymptotes today. Fun. We're also going to talk about some just fun graphs and some interesting things that happen with some of these graphs. So I hope you are ready. I hope you are excited. Wherever you are, whatever you're doing, the only thing that you really need to be successful here is something to write with, something to write on. If you were my student, this is section 8.4 from our textbook. Again, this is part 2. Part 1, you can go back and watch. The link will be in the description of this video. Watch that first. Here we go. Let's jump right in. Okay, so what I want you to see here is this is essentially the material we're going to look at today. Slant asymptotes. What the heck are those things? Hiatus points. What? And interesting graphs. Okay, I hope you're ready. Here we go. Let's have some fun. So example 1, f of x equals 2x squared plus 10x plus 12 all over x squared plus 3x plus 2. Okay, so the first step here is we're going to factor this top and the bottom. Okay, so the top we can factor out a 2. I need a little bit bigger font for you guys to see. Okay, all right, so we've got 2 times x squared plus 5x plus 6 on the top, all over x plus 2 times x plus 1. Again, if you do not know how to factor, this video is not the place where you're going to learn how to factor, okay? All right, so factor the numerator one step further. So that ends up being x plus 3 times x plus 2 all over x plus 2 times x plus 1. Now, hey, looky here. We've got an x plus 2 on the top and the bottom. Those are going to cancel out. When you have, listen very carefully, when you have a factor like this that cancels out on the top and the bottom, that is a signal to you that you have a hole in the graph, that you have a hole in the graph. And what that hole is called a hiatus point. It's called a hiatus point. It's a place on the graph where there's literally going to be a hole on the curve. Okay, now here, pay close attention. This is how you actually find let me make that a little bit smaller. This is how you actually find the coordinates of that hole. Okay, so you start by taking the factor that canceled out, x plus 2, and you set that equal to 0. And you solve that for x, you'd get x equals -2. Okay, now you take that and you're going to plug that in your new function, okay? So now we actually have a new function left over. So our new function here is 2 times x plus 3 all over x plus 1. That's the new function that we're going to use from this point moving forward, okay? So to find the y-coordinate of the hiatus point, we're going to plug that x value that we found in for x. So 2 times -2 plus 3 all over -2 plus 1. That gives me +1 times 2 on the top divided by -1 on the bottom. That gives me -2. So my hiatus point, watch this. The x-coordinate was -2. I got that by setting the canceled term equal to 0 and solving. And then I take that x value and I plugged it in the remaining function, what I have left over, and figure out what the y value is, and that's also -2. So on your graph, what you're going to do is you're going to go over to -2, -2, and you're literally going to put a hole there. You're going to put an open circle there. That's not -2, -2. That's -2, +2. You silly goose, you. There it is. Okay, that's better. -2, -2. That's the location of your hole, your hiatus point. Okay. Next, we're going to identify the vertical asymptote. Okay. Now, if you watched part 1 of 8.4, you know to find the vertical asymptote, we set that equal to 0, the denominator equal to 0. So with the denominator that we have left over, x plus 1, We set that equal to 0, and we get x equals -1. So let's get that on our graph. So vertical asymptote at x equals -1. Okay. Next, the horizontal asymptote. Okay. This is where we need to use our acronym Bobo Botten Eats DC. So if we look at this function, this is an Eats DC. Okay. If you need to make yourself a little note that's fine too. This is an Eats DC because the exponents are the same. So we divide coefficient on the top by coefficient on the bottom. So that's 2 divided by 1, which would be 2. Okay, so let's add that to our graph. Horizontal asymptote at y equals 2. Okay, okay, now the next thing that I'm going to do is I can tell pretty clearly that I'm going to have a branch that goes through this quadrant, which means the other branch is going to go through this quadrant. Now, it's a good idea on these to find your x and y intercepts. Okay, so let's find the x-intercept here. Okay, the x-intercept, remember we set the numerator equal to 0 and we solve for x. So that's 0 equals x plus 3, which will end up giving me x equals -3. So my intercept here, my x-intercept is, a point, -3, 0. So let's plot that on our graph. So x equals -1, -2, -3. So that's a real point. It doesn't have to be a whole. Okay. And lastly, let's do our y-intercept. So for the y-intercept, remember you make every x you see equal to 0. So that would be 2 times 3 is 6. 6 on the top. 2 plus, over 1 on the bottom, that'd be 0, 6 would be my y-intercept. Okay, so 0, 6 is my y-intercept. Again, I'm just plugging 0 in for x. Again, if this is going too fast, you probably need to go back and watch part 1 of this video series. Again, link in description. So let's plot that point, 0, 6, 1, 2, 3, 4, 5, 6. Okay, I feel really, really good to be able to draw the branch in quadrant 3 here. Okay. Again, remember that the asymptotes act like magnets. They draw the ends of those branches to themselves, okay? They're drawn to the asymptotes. Okay, and I would probably maybe make a table of values to find, I don't know, maybe one more point on here, okay? Maybe one more point somewhere up in this area so I could feel really confident about the graph I'm drawing. So maybe pick, I don't know, let's pick something easy. Let's do x equals 1. How about, okay? So we're plugging 1 in for x here. Remember, this is our new function, okay? So 1 plus 3 is 4. 4 times 2 is 8. So 8 on the top over 2 on the bottom. That gets me 4, okay? Let me get my pen here. So 1, 4. 1, 2, 3, 4 would be the location of that other point. You could pick another point if you want to, but I feel pretty good about that, especially because I know that the asymptotes draw the ends of this branch to itself. And that is a pretty good picture of this graph, okay? Make sure that your graph specifically shows the hole, okay? There's a hole in the graph. That hole is called a hiatus point, okay? Go back and watch that again if you need some pointers on what you do when you have a hiatus point, okay? Problem number 2, okay? Problem number 2 is, and I should tell you there's 5 different graphs I'm going to go through with you, okay? 5 different graphs just so you can keep track. Okay, here we go. First thing we're going to do is we're going to clean up the numerator as much as we can. So that's 3x times x minus 4 on the top. And we factor the denominator to x minus 3 times x plus 1. Okay, so as you look at this, there in this problem, there is not a there's not a factor that cancels on the top and the bottom. So for HP, hiatus point, we would say there's none. Okay, there is no hiatus point in this graph. Okay, so there is no hole. Okay, now vertical asymptotes, we do that next. Now for the vertical asymptotes, remember we set the denominator equal to 0 and solve, which is the fact that this is factored makes that really, really easy. We set each one of those equal to 0, and we get a asymptote at x equals 3, and we get another asymptote at x equals -1. So I'm going to go to my graph, and I'm going to plot those two lines. X equals 3. And x equals -1. So there's 2 vertical asymptotes here. So there's going to be 3 parts of this graph. There's going to be a part here somewhere, here somewhere, and here somewhere. There's going to be 3 branches to this graph. It's going to be awesome, okay? Like I told you at the beginning, man, we're going to look at some fun graphs today. Okay, next, let's do the horizontal asymptote. For horizontal asymptote, we use those acronyms that we learned in the last video, BOBO, BOTN, EATS, DC, okay? I look and I see that the exponents are the same, so this is another EATS, DC. So when the exponents are the same, we divide the coefficients, so that's 3 over 1, which just equals 3. So I'm going to add that to my graph as well. A horizontal asymptote at y equals 3. Okay. Now, the next thing that I would do here is I would find my x and my y intercepts to kind of get an idea of what's happening here. Okay, x-intercepts. So the x-intercepts, to find those, you set the numerator equal to 0. Okay, you set the numerator equal to 0. So that would be 0 equals 3x times x minus 4. Solve for x in each one of those, so we get x equals 0, and we get x equals 4. So there's actually 2 x-intercepts in this problem, 0, 0, and 4, 0. So let's plot those points on the graph. 0, 0, and 1, 2, 3, 4, 0. Okay, so there are my 2 x-intercepts. Now, the y-intercept, to find the y-intercept, let's make that purple. I like it all to match. Somebody out there appreciates that. The y-intercept, okay, we're going to, again, make every x you see equal 0, okay? So that would end up being 0 minus 0 on the top, all over 0 minus 0 minus 3 on the bottom. Well, 0 divided by negative 3 is 0, which we shouldn't be surprised because we already saw the x-intercept was 0, 0, okay, which means the y-intercept will also be 0, 0 as well. Okay, now we've got some serious work to do with the table here, okay? So I'm going to try to squeeze my table in right here, okay? So here we go. So on this table, we are going to pick some x values strategically to figure out what the heck is happening in this part of the graph. Okay, let's start with that one. So let's pick an x value that's kind of close to this asymptote. Nothing crazy. So let's start with maybe, I don't know, let's start with negative 2, okay? So when I plug negative 2 in for x, okay, you can simplify that. I'll let you work on that, okay? When you plug negative 2 in for x and simplify, I'll let you, again, pause it here and work on that real quick. But you end up getting 36 fifths, okay? Now, 36 fifths is a little bit more than 7, okay? It's a little bit more than 7. So let's plot that point, okay? So negative 1, 2, and then go up to a little bit more than 7. So 1, 2, 3, 4, 5, 6, 7, just a little bit above that, okay? Now, here's what that tells me. The fact that that point is located there, it means the branch up here is going to look something like this, okay? Now, if the branch up here looks something like this, that means the branch over on the far right is going to look something like this, okay? So let's figure out what's happening in the middle here. Okay, let's figure out what's happening in the middle. All right, so in the middle, let's pick an x value between negative 1 and positive 3. I don't know, how about we pick 2? Okay, let's pick 2. So when I plug 2 in for x, again, I'll let you do that. Okay, you don't need me to walk you through that. It's a pretty easy skill. Plug 2 in for x, pause it if you need a couple minutes. Okay. So after you've plugged 2 in for x, you should have gotten 6. Okay, you should have gotten 6. So when x is 2, y is 1, 2, 3, 4, 5, 6. Okay? So that's a very interesting situation here. Okay, that's a very interesting situation. So let's start with this outside far left branch. Far left branch we know is going to look like this. Remember that those ends of the branches are drawn to the asymptote like a magnet. Now, from 8.4 part 1, I also showed you that as a function approaches an asymptote from different sides, one arrow is going to go up and one arrow is going to go down. So what that means is as I approach the asymptote x equals negative 1 from the right side, that branch has got to be shooting down. Okay? It's got to be shooting down. Now let's start all the way over here on the far right as well, and let's draw a sketch of this branch. Okay? So likewise, as I approach x equals 3 from the right and the left, the arrows need to be going in opposite directions. So since from the right the arrow is pointing down, as I approach from the left, that arrow is going to have to go up. So think about a line where as I approach x equals 3, the arrow is going up, and as I approach x equals -1, the arrow is going down. Okay? Here's what a sample of that line could look like. Cool little curve there in the middle. Okay? Now, some of you may be having an issue with this point right here. You're like, Cozad, you told us that you can't touch an asymptote. Okay? Well, sometimes some of these functions actually do cross the horizontal asymptote. Okay? They actually do cross the horizontal asymptote. They will never, ever cross the vertical asymptote, but sometimes there's a little weakness on the horizontal asymptote that allows some of those functions to pass through. Okay? The biggest thing I want you to see here on this graph is that as you approach this asymptote, each one of them, the arrows go in opposite directions. Okay? That is a really good tool for you to remember when you're asked to draw these graphs. Remember that as you approach an asymptote, a vertical asymptote from the left and the right, most of the time those arrows point opposite directions. Sometimes they point the same direction, but I'll show you that in a few problems. Okay? So, next problem, number 3. Okay? Oh man, this is another great problem, guys. You were so lucky here. Okay? You're so lucky. So, step 1. Let's see if we can factor and find anything that cancels. So this becomes x plus 3 times x minus 1 all over, I'd factor out a -3, and I get x plus 2. Okay, nothing that cancels, so there is no hiatus point here. Okay, there is no hiatus point here. Vertical asymptote, set the denominator equal to 0 and solve. You get x equals -2. Horizontal asymptote, Bobo Botten eats DC. This degree is bigger on top, so this is a Botten. Okay, so if it's bigger on top, the N stands for none. There is no horizontal asymptote. Okay, but there is a unique situation that occurs. Listen very, very carefully. There is a unique situation that occurs when the degree on the top is exactly 1 degree larger than the bottom. So the degree on the bottom is 1, the degree on the top is 2. Again, there is something very, very unique that happens in these functions when the degree on the top is exactly 1 degree larger than the degree on the bottom. It's critically important that you hear me say that. The degree on the top has to be exactly 1 degree larger than the bottom. When that happens, when the degree on the top is exactly 1 degree larger than the bottom, you have what's called a slant asymptote. Some books and some teachers call this an oblique asymptote. We call it slant, but just know that some people call it oblique, slant or oblique, okay? And here's how you find the oblique or slant asymptote. You're going to take the denominator and divide it into the numerator using long division, okay? Now, before you moan and complain like, oh no, not this again, okay, it's actually pretty straightforward and easy because you don't even care about the remainder. You don't care about the remainder. So if you need a refresher on this type of division, we do first divided by first. So that's x squared divided by -3x. Well, when I do that, I get -1/3 x. Now we multiply. -1/3 x times -3x is x squared, and that's going to be plus 2x. After we do the multiplication, we subtract each column, and we end up getting 0x minus 3. So repeat the same process. First divided by first. 0x divided by 3x is actually plus 0. Okay? Now, once you get here, you can actually stop because you don't care about the remainder. This is going to have a remainder, but we don't care about it. The the equation of our slant asymptote, let me slide that down a little bit more, is going to be the equation that you have in your quotient. So that's going to be y equals -1/3 x plus 0, but plus 0 isn't really important. It's not necessary there, okay? So let's go through and let's plot on our graph what we know already. So we know that there's a vertical asymptote at x equals -2. And this slant asymptote is at 1/3 x. So start at the y-intercept of 0 and apply a slope of -1/3. So that's up 1, left 3, up 1, left 3. You could also go down 1 from the origin and right 3, down 1, right 3. And then you're going to draw that as a dashed line, just like we would for any other asymptote, okay? Now, this is pretty cool, okay? So all this does is this, I'm either going to have branches here and here, or you could have a scenario where I have a branch here and here. So to help us kind of identify where these branches are going to be located, let's find our x-intercept and our y-intercept, okay? To find the x-intercept, there's actually 2 here because I take the numerator and set it equal to 0. So when I do that, I end up getting x equals -3 and x equals +1. So when I write those as points, that's -3, 0, and 1, 0. So let's plot those on our graph. So we said -1, 2, 3, 0, and +1, 0. Okay. Now we're going to find the y-intercept. Okay, let's find the y-intercept and see what we have. Okay, so for the y-intercept, you make all the x's that you see 0. So this goes away, this goes away, this goes away. So what you'd have left is -3 over -6, which would be +1/2. So our y-intercept is going to be 0, 1/2. Okay. Now, because the location of these points here, it tells me that I'm going to have a branch that does something like this and something like this, okay? So now let's sketch those branches. So be very, very careful and remember that the branches are drawn like a magnet to the asymptotes, like so. So the only thing that changes with this graph is the fact that the slant asymptote makes it look a little interesting. The other thing that changes here, my voice cracked just a little bit. I hope you didn't hear that. Don't go back and listen to it, okay? The other thing that changes here is the range, okay? We haven't talked about domain and range much in here today, but the range, as we look at all the possible y values, since there is no horizontal asymptote, if you were ever asked the range on this function, okay, you would say that the range is all real numbers from -infinity to +infinity. There is not a single y value that you can't achieve. Okay? Man, that's a good one. All right, number 4, 2 more. We're almost done. Okay, we're almost done. I know time flies when we're having fun. Okay, so first step here is to do some factoring. So we get 2 times x minus 3 on the top. Factor out an x on the bottom, and you get x minus 3. Those cancel, so guess what? There's going to be a hole. Get excited. Okay, so let's find the coordinates of that hiatus point. Okay, so we did this back in example 1. Let's see if you remember. Take that factor that canceled and set it equal to 0. Solve for x, you get x equals 3. Now our new function, f of x, is 2 over x. So we're going to take that x value and we're going to plug it in the new function. So we get 2/3. So the location of our hiatus point is going to be 3 2/3. So what I like to do is go straight to my graph, and I like to put a hole there right away. So it reminds me that there's a hole there, okay? Now, vertical asymptote. Set the denominator equal to 0. That's so easy. It's going to be x equals 0. So let's add that to our graph. Vertical asymptote at x equals 0. Okay? Horizontal asymptote. Bobo Botten eats DC. This degree is bigger on bottom. So there is, the asymptote is y equals 0. Bobo, bigger on bottom, 0. So we've got our horizontal asymptote at y equals 0 as well. Now all I've got to do is let's find the x-intercept and the y-intercept. Okay, so the x-intercept, that's going to make somebody uncomfortable that I broke my pattern of purple, so let's just change that for you super type A people. You're welcome. That's for you type A people. Okay, so the x-intercept, we set the numerator equal to 0. Well, think about it. Can you set 2 equal to 0? There's nothing to solve for. So if there's nothing to solve for, there is no x-intercept. On the y-intercept, we set all x is equal to 0 and solve. Well, here's the problem. If we set this x equal to 0, we would have to divide by 0, and that's no bueno. We cannot do that. So there is no y-intercept either. Okay? So now what I'm going to do next is make a table of values and try to identify where these two branches of the graph are going to be located. Okay? All right. Let's pick an x value. Let's try x equals 1. Okay? When you plug a 1 in for x, that's easy. You just get 2. Okay, so let's graph that. At this point, guys, I feel pretty comfortable to be able to draw this first branch here. Okay, remember that it passes through the hole, but it doesn't actually cross through it. Make sure it's very clear to see that is, in fact, a hole. Okay. Okay, so now, based on the location of the first branch, I know there's going to be another branch somewhere over here. But let's find a few points on there so we can make sure we draw it pretty accurately. So let's do x equals -1. That ends up giving me -2. And let's do, I don't know, let's do one more. Let's do x equals -2, which gives me y value of -1. -1, -2, -1. So there, I feel pretty good about being able to draw that branch as well. So remember that as you draw these branches, the ends are drawn towards the asymptotes like a magnet. Okay? Pretty cool. One final problem together. Here we go. F of x equals x plus 1 squared times x minus 3 all over x plus 3 times x minus 1 squared. Now this one's already factored for you, okay, to be nice. Okay, it's already factored for you. Now, notice there's nothing that cancels out here, okay? So there is going to be no hiatus point, okay? No hiatus point. Now, for the vertical asymptotes, okay, there's going to be more than one. Set each element in the denominator equal to 0 and solve, okay? We get x equals -3, and we get x equals 1. Now, my students, you're going to have to remember all the way back to chapter 5. What do we call zeros that happen more than once? So x minus 1 actually happens twice. We'd have 2 of those. So we don't have to write it twice, but remember chapter 5 when we talked about multiplicity, okay? We'd say that x equals 1 with a multiplicity of 2, okay? With a multiplicity of 2. I should write that a little bit better. We'll say with a multiplicity that equals 2. That is going to be a really important thing to remember, okay? We'll come back to that. That has an important effect on the graph, okay? The horizontal asymptote, okay? This one's a little tricky to figure out if it's a Bobo, a Botten, or an HDC. You don't actually have to multiply these out, okay, to figure out what is going to happen here. You've got x squared times x in the numerator. X squared times x would give you x cubed on the top, and then a bunch more stuff that we don't have to multiply. And then the same thing on the bottom. We'd have x cubed on the bottom as well, okay? X times x times x would get us x cubed. So when you see it like this is an HDC. The exponents are the same. So when the exponents are the same, we divide the coefficients. So 1 over 1 is 1. Y equals 1. Okay? Now, let's do the x-intercept and the y-intercept. So the x-intercept, remember you set the numerator equal to 0 and you solve. So here you get x equals 3 and you get x equals -1. Again, remember to chapter 5 with a multiplicity of 2 because x equals -1 will happen twice. Again, this is going to be a key part of our graph as well. It's going to help you draw this accurately. Okay, so let's write those out as points. So that's 3, 0, and that's -1, 0. Okay, and lastly, let's find our y-intercept. To find the y-intercept, you set each x equal to 0 and you solve. So I'll let you do that. You got to plug and chug just a little bit on that. Do a little bit of work on that to plug 0 in, and you should end up getting negative 3/4. Negative 3/4. Okay? All right, now let's start building our graph. This is the most fun graph we've done all day long. I'm so excited that we waited to the end to do this one. So draw an asymptote at x equals negative 3, and draw an asymptote at x equals 1. And then our horizontal asymptote at y equals 1. Okay, then let's plot our x-intercepts. So I have one x-intercept at 3, 0, so over here, and one at negative 1, 0. Okay. Now, here's the deal. You know that there's only two places where these curves are going to cross the x-axis. Right here and right here. So, if you're really wise, you little detectives, okay, we know that this branch over here on the right is going to look like this. We know that because it's drawn. We already found a point in this little section, and we know that the ends are drawn towards the asymptotes like magnets. Okay? Here's what else I know. I know that since there can't be another x-intercept on this section, what does that tell us about the branch on the far left? It tells us that it can't be down here. It's got to be above that horizontal asymptote. Okay? So just for fun, let's pick a point, an x value, and see what we get. So let's plug negative 4 in for x. That's kind of an ugly one. If you plug negative 4 in for x, it's kind of hairy, but you've got a calculator to help you with that. You get about 2.52 when you plug a negative 4 in for x. Okay? And what that helps us see is that when I go to negative 4 for x, I go up to about 2.5 on the y-axis, or on the y value. So that tells me that this branch over here is going to be above the horizontal asymptote. Remember that the ends are drawn towards the asymptote like magnets. Now, the middle part is the best. It's the best part, okay? Two things about multiplicity that I want to talk to you about, okay? Let's first talk about the multiplicity when the vertical asymptote has a multiplicity of 2. Just a few graphs ago, I told you that as branches approach asymptotes, they always go in opposite directions. But I told you that there's one particular circumstance where they don't go in opposite directions, they actually go in the same direction. And that is the scenario that we have right here. When you have a multiplicity of an asymptote that is 2, as you approach that graph from both sides, that asymptote from both sides, those arrows are actually going to point in the same direction. Again, because the multiplicity of that vertical asymptote was 2. How do you know the multiplicity is 2? Because when we set that denominator equal to 0, we had 2 of the x minus 1 terms. So that's how we know that the multiplicity was 2. Now, the other factor here is that the multiplicity of this x-intercept is also 2. So again, think back to our chapter 5 where we talked about multiplicities of zeros. When the multiplicity is even, in this case 2, what happens at that 0? Is it a bounce off the graph or a snake through the graph? Hopefully you remember that it's a bounce off the graph. So here's what I know. Let's put all this together. Okay, it's a lot of information. Because the vertical asymptote has a multiplicity of 2, I know when I draw this that the arrows have to be going the same direction. So I know that they both have to be pointing down like this. I also know that because this x-intercept has a multiplicity of 2, the graph's going to hit and bounce right back off and go the other direction. Now, should we be surprised that the arrows go opposite directions on the asymptote x equals negative 3? The answer is no, because its multiplicity was only 1. And if the multiplicity is only 1, the the branches go opposite directions as they approach that asymptote. But when the vertical asymptote has a multiplicity of 2, like that was the case with x equals 1, we get a scenario where the branches both shoot off in the same direction as they approach that asymptote. Whoo! Whew, that is a lot of material. That's heavy lifting. You might need to just take a break and go for a walk, get a drink, get some popcorn, do something, because man, that was a lot. That was a lot. I hope that this was helpful for you. It's a lot really, really fast. I know a lot of you are going to tell me that you need more help, and that is fine. Okay, go back and rewatch some parts of this, and I think every time you watch a new part of it, you're going to pick up something new as well. You guys are awesome. Thank you so much for staying with me. Those of you that are here with me to the end, you're the real ones. You're the ones that I appreciate the most, and I can't wait to get after it in our next video.